So today we're going to look at Newton's second law, otherwise known as force equals mass times acceleration. Things that affect the acceleration of an object, in this case a car, are the force acting on it, the resultant force, meaning the vector sum of the forces, meaning not one individual force necessarily, but once we've decided all the forces acting together, what is the overall resultant force that they have on the object? Okay, so we can see, obviously, mass is measured in kilograms, acceleration, meters per second. How much is the meter per second? How much is the velocity changing every second, which gives us meters per second squared? And force is obviously measured in newtons. Here we have the same force being applied to two objects, one with a smaller mass, yielding a larger acceleration, and one with a larger mass, yielding a small acceleration. This is the same scenario playing out here, where we're essentially saying that the same force is being applied to the two objects, the bowling ball having a much larger mass, and hence its inertia is meaning that it's not going to accelerate as much. Naturally, in this scenario, you might presume that there's lots of heavy things. It's a very massive lorry at the top here, but here we can kind of see sorts of scenario where we're saying we've got two objects and they have the same mass, but the fuel cell is providing a much greater engine force, hence the lorry is accelerating at a greater rate. Okay, so if we just draw your attention to the top right here, if we rearrange the formula to make acceleration the subject, force, which equals force over mass, this is the best way to make sense of the formula. Is we're saying if we've got double the force, then we're going to double the acceleration because the force and the acceleration are directly proportional to each other. Whereas the mass being on the denominator means if we double the mass, we're going to halve the acceleration, the two being inversely proportional to each other. And what I also want to highlight here is the similarities between the force equals mass times acceleration and the formula for weight, mass times gravity. With weight being a force measured in newtons, the force that a mass interacting with a gravitational field, the force that will pull on that object, and so is extremely similar, is basically the same thing. And the G value, which is the amount of newtons that act on a kilogram, but if you notice the value an object will accelerate in the absence of air resistance is the same value. So the G value also represents an acceleration towards Earth. And I'm going to finish on an example here. So we've got a 2 kilogram object. It's gathered an air resistance of 9.6 newtons. I didn't choose that by accident to make my numbers easier to play with later. And so we've got a 2 kilogram object. It's been falling for a little bit of time. It's not yet reached terminal velocity. So the first thing I'm going to do is I'm going to use the weight formula to work out what is the force of weight acting on. That's 19.6 newtons. So I'm taking the 2 kilograms, timesing it by the G value of 9.8, getting 19.6 newtons. And now the resultant force, we might say it's the vector sum of the forces, vector meaning it's directional dependent. So you can see the two forces here are acting in opposite directions. So the difference between them will tell me the resultant force. So in this case, it's going to be 10 newtons in the downwards direction. Whereas obviously if the forces are acting in the same direction, you would add them up. And so now I'm going to apply my acceleration formula. And if I rearrange it, so whatever's the way I say it, if whatever's on the numerator, you bring it to the denominator when it goes to the other side, as long as you don't have any pluses or minuses, that always works. And we've got acceleration equals force over mass. So I take my resultant force of 10 newtons divided by my 2 kilograms, give me an acceleration of 5 meters per second squared. Obviously, the object will naturally speed up and the force of air resistance will increase up until the point that it equal and opposite the weight, and by which our resultant force will be 0. If you divide zero by anything, you will get zero, and that will be the point where the acceleration is not accelerating, it's moving at constant speed, terminal velocity.